In this lecture, we're going to discuss another consequence of adding non-volatile solutes to a solvent, and that is boiling point elevation. So in the same way that adding a non-volatile solute will lower the vapor pressure of a solution relative to the vapor pressure of the solvent all by itself, adding non-volatile solutes is also going to increase the boiling point of a solution compared with the boiling point of the pure solvent all by itself. And this is because if you can imagine the non-volatile solute particles, they don't want to vaporize. So you are going to have the solution have a higher boiling point, a higher temperature that is going to result in the same amount of vaporization. We can show this phenomenon using a phase diagram. So in a phase diagram, as you'll recall, we plot pressure on the y-axis and temperature on the x-axis. And this is a way that we can delineate the differences between the phases. So solid is going to be at high pressure, low temperature. Liquid is going to be in between, and the gas phase is going to be dominant at higher temperatures and lower pressures. Now, what happens when we add a non-volatile solute? Well, when we add a non-volatile solute, the phase diagram would look different. Okay, so this would be a solution with the non-volatile solute. So if the black lines refer to the pure solvent, okay, the phase diagram for the pure solvent, the green line refers to the solution with a non-volatile solute added to it, to that pure solvent. So you can see what happens. Remember that at 1 atmosphere, okay, so let me draw a kind of line over here. Let's just say that this is 1 atmosphere. So at a pressure of 1 atmosphere, we have a temperature that we call the normal boiling point. So for the pure solvent, the normal boiling point would be here on the temperature axis. By contrast, okay, I need to modify my axis a tiny bit, so let me just fix that. So by contrast, just extending my axis a wee little bit, the normal boiling point for the solution with the non-volatile solute in it is going to be higher. So we're going to have a difference there that I'm going to call delta T. And delta T represents the boiling point elevation that results from adding that non-volatile solute. Okay, so the boiling point elevation, raising the boiling point, delta T, is going to depend on what the solute is and how much of it there is actually, and the concentration. And of course, this is also going to vary depending on what solvent you have. So the extent of delta T is given by the product of a constant that I'm going to call Kb times the molality of the solution, M. So I want to define what each of these parameters is. Kb is the boiling point elevation constant. It varies according to what you're talking about, and I want to really emphasize here that it refers to the solvent, not the solute. So when you're looking up a Kb value, you are doing so for the solvent, not the solute. For example, the Kb of water, if you look it up, is 0.51 degrees Celsius times kilograms times moles. Now notice those units. It's reciprocal molality. And that's because the little m in this equation refers to the molality of the solution. Remember that molality is the moles of solute over the kilogram of solvent. So if you were wondering when you were ever going to use molality units, here you go. You use them to figure out the delta T for boiling point elevation. So molality of the solution multiplied by the boiling point elevation constant for the solvent will give you the extent of the boiling point elevation. Now, just as we have boiling point elevation when we add non-volatile solutes, adding non-volatile solutes will also depress the freezing point compared with the pure solvent. Now, I hope this makes sense. If you imagine a pure solvent like pure water freezing, you're imagining the intermolecular forces kind of bringing those water molecules together as solid ice, right? If you have a solute in there, you're going to disrupt those forces. And that is going to depress the freezing point. It's going to mean that you need a lower temperature to make ice. This is the principle behind salting roads. We throw salt out on the roads to depress the freezing point and make the ice melt, okay? If you put salt in water, then that water will freeze at a lower temperature, okay? So that's the freezing point depression is the principle behind which the whole idea of salting roads is based. All right, so the extent of freezing point depression is given by a very similar equation. Delta T equals Kf times the molality. Once again, we're dealing with molality. Kf is the freezing point depression constant. And just to give you an example, the freezing point depression constant for water is 1.86 degrees Celsius kilograms per mole. So let's do an example. Boiling point elevation and freezing point depression are pretty similar calculations. So I just want to practice using a freezing point depression example. What's the freezing point of a 50 gram mixture of ethylene glycol, which is an organic compound that has a molecular weight of 62 grams per mole, and water? Okay, so can we figure out what the freezing point of this is? And let me just give you a hint. You're going to need the freezing point depression constant for water, which I gave you a moment ago, as 1.86 degrees Celsius kilograms per mole. All right, so if we want to figure out the freezing point, we need to calculate the delta T. So we're going to need the equation that delta T equals Kf times the molality of the solution. I have the Kf, 1.86 degrees Celsius kilograms per mole, so I need to figure out the molality of the ethylene glycol. Now, since I have the Kf for water, water is going to be the solvent here, because remember, Kf pertains to the solvent. And the ethylene glycol is going to be the solute. So the molality of the solution has to be the number of moles of ethylene glycol divided by the kilograms of solvent, which is water, kilograms of H2O. So I know the kilograms of H2O, right? I have 50 grams and 50 grams. So I just need to, for the denominator, I need to convert that 50 grams to kilograms. And for the numerator, I need to convert the 50 grams of ethylene glycol, 50 grams of ethylene glycol to moles. I have the number of moles, because they gave me the molecular weight here. I can multiply this by the reciprocal of that molecular weight to get the number of moles of ethylene glycol. So that's going to be in the numerator of my molality. And in the denominator, I have 50 grams of water. So that's 0.050 kilograms of water. So I can cancel out my grams, and I'm left with a molality value in moles of ethylene glycol per kilograms of water. If you do that arithmetic, you should get a molality of about 16 moles per kilogram. Now, I'm going to take that 16 and plug it into the equation to figure out the freezing point depression. So the freezing point depression, delta T, is going to be equal to the Kf, which is 1.86 degrees Celsius, kilograms per mole. That's the Kf for water, multiplied by, oh, sorry, I wrote the units down incorrectly. So it's degrees Celsius, kilograms per mole. And I'm going to multiply that by the molality, which is 16 moles per kilogram. All right, the units are important because notice what happens. The kilograms cancel, the moles cancel, and I'm left with a delta T in degrees Celsius, which is exactly what I want. And if you do the arithmetic here, it comes out to be 30 degrees Celsius. Now remember, this is the freezing point depression. So I need to take this value and subtract it from the normal freezing point because I want to figure out what the freezing point of this solution is. So the freezing point of the solution is going to be the normal freezing point minus the freezing point depression that I just calculated. All right, so I can't forget to do that. Of course, for water, the normal freezing point is 0 degrees Celsius. I'm going to subtract the 30 degrees Celsius from that, and that gives me a freezing point for this solution of minus 30 degrees Celsius. Now, I want you to be amazed at how dramatically low that is. And this makes a whole lot of sense because this example that I just gave you, of course, is antifreeze. Ethylene glycol is one of the ingredients that you can use to make antifreeze. And you can see that you dramatically reduce the freezing point of water when you add ethylene glycol to it. So this makes a very effective antifreeze. Another example we can do using the freezing point is you can calculate freezing point depression or measure freezing point depression to help you identify the molecular weight of a mystery compound. So in this example, we have a solution containing 5 grams of an unknown compound in 60 grams of water. And you can measure experimentally what the freezing point is. You find that it freezes at minus 1 degree Celsius. So from there, can you figure out the molecular weight of the compound? Well, you know that the freezing point depression is 1. Okay, because the new freezing point is minus 1, so that means that delta T is 1. And that's going to be equal to that Kf. We're still talking about water, so it's the Kf from before times the molality. So I can calculate the molality by taking 1 degrees Celsius divided by 1.86 kilogram degrees Celsius per mole. Mole flips to the top, and that gives me a molality of 0.54 moles per kilogram. Now, if that is my molality, I can figure out what the molecular weight is going to be. Remember, I'm asked for molecular weight, and molecular weight is going to be in units of grams per mole. So I need to figure out what this molality would be in grams per mole. Now, the other piece of information that I know is that I have 5 grams of the unknown in 60 grams of water. So here I really need to think about what molality means. That molality value of 0.54 moles per kilogram is going to be equal to the number of moles of the solute that I have, the mystery compound, over the number of kilograms of water. I know how many kilograms of water I have, right? I have 60 grams, so I can convert that to kilograms. And then on the top, I need to figure out how many moles of water, moles of this mystery compound I have. I know that I have 5 grams of it. So I have 5 grams of my mystery compound. And I'm going to multiply that by the reciprocal of its molecular weight. Moles over X grams. What I'm interested in finding out is that molecular weight of my mystery compound. So I need to, by doing this, I can solve for the reciprocal of the molecular weight, and then I can take 1 over that to solve for X. So if I rearrange this equation, I find that the reciprocal of the molecular weight uh, can be then converted to 155 grams per mole. So this example shows how you can use freezing point depression to figure out the molecular weight of an unknown.